So this is one of the oldest known whales. Now this is the truth, okay? It's a whale. This is a mammal. Okay, this is a baleen whale, an ancient baleen whale. All right. Shonosaurus is a genus of ichthyosaur. At least 37 incomplete fossil specimens of the marine reptile. It's not a reptile. It's a mammal. It's an ancient baleen whale. Have been found in Luning Formation of Nevada, USA. This formation dates to the late Carnian age of the late Triassic period, 237 to 227 million years ago. Okay, this is an ancient whale. It's one of the oldest, largest mammals. Now here's Shastosaurus. Okay, they're an ichthyosaur species. They're both toothless. Okay. Shastosaurus was highly specialized and differed considerably from other ichthyosaurs. It was very slender in profile. The large specimens had rib cage slightly less than 2 meters, 6.6 feet, despite a distance of over 7 meters, 23 feet between its flippers. Due to its unusually short, toothless snout compared to the long-toothed dolphin-like snouts of most ichthyosaurs, okay? Dolphin-like snouts of ichthyosaurs. Now, all right, now here's Archaeoceti. Okay, these are all different species of Archaeoceti. The whale, ancient whale, Pakicetus, Ambulocetus. Okay, here's an ichthyosaur. All right, they got the same orbitals. Their elongated beak. Also, ancient baleen whales are suction feeders, or they're bottom feeders. It is proposed that Shastosaurus was thought to be a suction feeder, feeding primarily on soft-bodied cephalopods, although current research indicates ichthyosaur jaws do not fit the suction-feeding profile. Okay, it's a baleen whale, all right? They're half right. It's not necessarily a suction feeder like an algae eater is, but it does feed on plankton, like baleen whales do. They don't have teeth. Okay, the Odontoceti. See, this is Mysticeti. This is ancient Mysticeti right here, more or less. It's ancient Mysticeti. And eventually they're going to evolve teeth. See, again, here they go lying about the return to the sea shit. Okay, ichthyosaurs thrived during the Mesozoic era based on the fossil evidence. They first appeared 250 million years ago, and at least one species survived until 90 million years ago, technically around 70 to 60 million years ago, technically, into the late Cretaceous. During the early Triassic epoch, ichthyosaurs evolved from a group of unidentified land reptiles that returned to the sea, just like they say with the ungulates that return to the sea to become mammals or whales. The mammals just happen to appear. Look, they had to come out of the ocean in the first place, okay? This is how I know they're full of shit. When they say something, return to the ocean. Evolution worked backwards. When they try to tell me that evolution started working backwards, I know they're full of shit, all right? In a development similar to how mammalian land-dwelling ancestors of modern-day dolphins and whales returned to the sea millions of years later. See what they're doing? They're repeating the same lie because they know that the ichthyosaur is actually a whale, okay? They're hiding evolution from people, and they're doing it right here. They're either doing it on purpose or they don't friggin' realize it. Ichthyosaurs resemble both modern fish and dolphins, okay? They have a tail like a dolphin, but they have fish-like resemblances because they're evolving into mammals, Yes, mammals evolved from fish, but we didn't go from fish onto the land because we give live birth and fish lay eggs, okay? So we had to have come from the ocean as a four-chambered heart, placental mammal, okay? So this ichthyosaur lived in the water with the dolphins, okay? Or with the fish, and eventually became mammalian. And it stepped onto land, and the fish also stepped onto land. Two lineages. You got the egg-laying lineage, and you have the placental lineage. All right, now here's the mud skipper. This is where the fish wanted to walk on land, okay? This is where the beginning of the evolution. See how they look like frogs? See how much they look like frogs? That's not just a coincidence, okay? The amphibians are important in understanding evolution, technically. Really important. The salamander especially. The salamander's vertical spine and its regenerating abilities are very important in understanding evolution. The hip bone of a frog is very important in understanding bipedal evolution. So the egg-laying lineage wanted to walk on land. What's it do? It ends up growing, adapting limbs like a salamander, and a hip bone like a frog, and a spine altogether like a caecilian, you know? First, you're going to have a spine. You have to have that backbone. Then you're going to start growing the limbs. Then your limbs are going to get a little bit better so you don't just crawl. You can actually jump. Eventually, it's going to want to stand up, okay? And you're going to get, in this lineage of egg layers, mammals, but not like placentals. They're all going to be birds, you know? They're going to have warm-blooded, four-chambered hearts, and they're going to be platypus. And this is why the duck-billed platypus and the duck are related, because they're in the egg-laying lineage. You see what I'm saying? The whales, on the other hand, they want to walk on land too. And they pass their genes, adapting their little flippers, their arms, to be able to crawl out on the land. You see what I'm saying? And that's why the walrus is such a significant animal. Now look at the manatee and look at the walrus. Look how closely look at the close resemblance of these two animals, okay? And the genomic studies on the walrus are lacking. And I wonder why. I really wonder why. So, I'm just throwing this out here, all right? So the mammals evolved in the water first from the fish. You see what I'm saying? And the ichthyosaur is that common ancestor of mammal and whale that we're looking for, but we got it named wrong twice. Ichthyo is fish, and saur, or saurus, is lizard. So we got it named wrong twice. Now, are they doing that on purpose because it's named wrong twice, or is it literally they're just naming it wrong twice on accident? You know? Because, I mean, that's just suspicious all along when I think about it, you know, in my opinion. So, if they got it named wrong on purpose, then that's, you know, that's the problem. But if they have it on an accident, they need to change it to a mammosaurian, because it'd be lizard-like, I guess, but it's a mammal. You know, it's not actually a reptile. It's not a fish either. And they're actually ovoviviparous. They give live birth like a marsupial would in a way, you know. They carry the eggs in their bodies and then they hatch live birth, kind of like some snakes do. So this is a mammalian trait, you know. They don't lay eggs, they give live birth. And eventually, reptiles will evolve a four-chambered heart. And the only reptile that's a true reptile that has a four-chambered heart is the crocodile or the alligator. That species, that order. See, Komodo dragons and other large lizards only have a three-chambered heart. Technically, when you think about it, in this sense, they're still in a amphibious reproductive stage. You know, they still have a three-chambered heart, just like amphibians. I call them protophibians. But more or less, the true reptile is a crocodile or an alligator, because that's a four-chambered heart and it's cold-blooded. And in that same egg-laying lineage, you have a four-chambered heart and warm-blooded. So in this lineage, here's the duck-billed platypus. It's got four-chambered heart. It's the fish's version of a sauropod, or a tetrapod, which is four limbs here, walking on four limbs, a tetrapod. It's the egg-laying lineage's version of a mammal tetrapod, okay, with a four-chambered heart that's warm-blooded. And the bipedal version, a theropod, is the duck, okay? Just like the frog has the hip gene, this is going to be where the hip gene starts to evolve. I mean, well, it not starts to. I mean, it's been evolving for millions of years. And that's why you have theropods, because they evolve from an amphibious hip gene, basically, an amphibious hip gene. And they walk upright, two legs. But it's warm-blooded, four-chambered heart, and lays eggs. See, technically there are only 3 amphibians. Now there are different species of these, hundreds, thousands, hundreds, but the hip gene here is evolved, and the legs are more for jumping instead of crawling. You see what I mean? Although they can walk too, frogs can. But this is a gene here, and this is a gene here, you know? And this right here is basically just the spine. Now this is a reptile, not an amphibian. But this is analogous to what happened to the amphibians that the reptiles can actually do. I call this, what happens to the reptiles, stagnant evolution. Okay? See how it's growing legs there? Snakes, sometimes they have legs. See? They grow legs. They'll actually adapt or mutate a legs, but there's no purpose in it. It's like stagnant evolution is what it is. You know, everything's complacent. The world's trying to adapt, you know, but there's no really strange, harsh variations to adapt to right now, you know, so it's stagnant. But in early Earth, when the Sicilian, these things here, they started to do the same thing, okay? They adapted and grew limbs, you know, which would ultimately evolve into what is the salamander. And of course, there's going to be variations in thousands of species of these, but eventually a hip gene's going to evolve. And these guys here, technically, can steal each other's genes, okay? You can have hybrids of these animals. So when you have a tetrapod and a theropod, and you have a hybrid gene or a genetic convergence, then you have a sauropod. Okay? It's a long-limbed animal. It gets the long limb gene and the hip gene in all 4. You see what I'm saying? In all 4 limbs. It inherits this through just genetic convergence of these 2. That's why amphibians are so important. That's why we study amphibians in school and for years. That's why everybody dissects a frog most generally, or almost everybody. I'm just saying this. That's the significance of it. Okay? They know there's a significance in understanding frogs and salamanders, amphibians. They know there's something there, I think. And they either are teaching people to, you know, these things to see if somebody might figure something out, or that it's really important in understanding evolution, you know, to understand amphibians and how diverse they are and how they can adapt and their genetic diversity.